So previously we have been successful in finding power series expansion for xcot x, tan of x, and x times the cosecant of x in terms of Bernoulli numbers, which are given by this generating function here, so x over e to the power of x minus 1. And we tried to do the same thing with sec of x, but we were not as successful as for these three functions. And so we would like to perhaps find some numbers other than Bernoulli numbers, which will enable us to give a convenient expression for sec of x. So we have to go back to the beginning and realize that we were led to Bernoulli numbers and this generating function here by trying to sum this series zeta of 2k when k is a positive integer. And so perhaps this means that we are going to have to consider a series other than zeta of 2k in order to be led to these mysterious new numbers, which will enable us to sum the second function to express it as a power series, that is. And so and then when we think further, we realize that we have obtained this expression for zeta of 2k by making a very bold assumption that the sine function can be factorized in the same way as polynomials. So we have not proved this in this video, but we have obtained certain results which gave us some confidence in the truth of this result. So we are not going to prove this in this playlist. This will be reserved for the playlist on complex analysis. However, we can make the corresponding assumption for cosine of x, which is that as cosine of x has roots plus or minus pi over 2, plus or minus pi over 3, plus or minus 5 pi over 2, so we are going to try to factorize cosine of x as if it were a polynomial, and we would find this expression for the cosine of x. And now let us cavalierly try to repeat what we did for sine of x with cosine of x when trying to sum zeta of 2k. And so we take logarithms. So we are going to work with these two series simultaneously. So when we take logarithm of an infinite product, it becomes an infinite series of logarithms. So very well, and then we are going to differentiate both of these. So the first one gives us a partial fraction decomposition for the cotangent, while the second one gives one for the tangent function. So these are the two partial fraction decompositions. And now we are going to look at these two series carefully, and something that is suggested to us is to rewrite x over 2 for x to make the two series more alike in a way. And when we do this, we find that we obtain the following two expressions. And now the natural thing that is suggested to us is to add these two series. And when we do this, we find a really nice expansion for tan of x over 2 plus cot of x over 2. So, but now we are going to consider this left-hand side trigonometrically and try to express it more simply. And when we do this and we use the various trigonometric identities, we eventually find that tan of x over 2 plus cot of x over 2 is equal to 2 over sine of x, which means that we have obtained a really nice series for the cosecant of x. So this is what we have found so far by making our assumptions. And we can rewrite each of these terms here, so we can decompose them into partial fractions as follows. And very well. And however, we realized that we wanted to expand the secant of x. But sine is related to cosine by sine of pi over 2 minus x equals cosine of x. So we replace the x by pi over 2 minus x in this expression. When we do this, we find that the secant of x can be rewritten in terms of these infinite series of partial fractions as follows. And we are now going to regroup these. So we group these two terms and these two terms and these two terms because they are very similar. Their denominator is very similar. And when we do this, we find this really nice expression for sec of x. And now we can recombine these two partial fractions in each bracket to find this expression for the secant of x under our assumptions about the factorization of cosine and sine. And we now are going, since we were looking for certain series corresponding to zeta of 2k to sum, we are going to expand each of these terms as an infinite geometric progression. And we are going to make, so we are going to simplify each of these expressions to make the first term equal to 1, except that we are going to multiply by these coefficients which proceed by this very simple law. And when we expand each of these as an infinite geometric progression, this is what we found for the second function. And of course, now the thing that we would like to do is to invert this double sum. So, and regrouping the sum by powers of x. And when we invert it, this is what we find for the secant of x. So we have discovered these mysterious series which we had to sum to find numbers corresponding to the Bernoulli numbers, which would enable us to expand the secant of x. And now we have to sum these series. And so if we denote the secant of x by these numbers E naught, E sub 2, E sub 3, E sub 6, and so on in emulation of the Bernoulli numbers, then we obtain these closed form expressions for these series here, when k is greater than or equal to 1. And now we are going to try to, so because so far our results have rested on the assumption that sine and cosine can be factorized as polynomials, we need to try to confirm certain of our results in ways which do not involve making any assumptions. So when we actually carry out division by writing sec of x equals 1 over cos of x, we find that E naught is 1. So if this formula is indeed correct, this would mean that 1 minus a third plus a fifth minus 1 over 7 and so on equals pi over 4. And so we are going to prove this without making any assumptions to give us more confidence in the truth of this result here. So to do this, the natural thing to try is to assign powers of x to each of these terms. So we define this function f of x as follows. And we differentiate it to find that it can be summed as an infinite geometric series, which is 1 over 1 plus x squared. And however, this reminds us of the arctangent function. So let y be the arctangent of x, where x is restricted between minus pi over 2 and pi over 2, so that this is well defined. Then x is equal to the tan of y, and dx by dy is equal to sec squared of y, which can be expressed as 1 plus tan squared of y by the Pythagorean theorem, and this is just 1 plus x squared. So that dy over dx is 1 over 1 plus x squared, which is this derivative f prime of x. So that f of x itself is the arctan of x plus some constant of integration. But from the definition of f of x, we find that f of 0 is 0, so that c is 0. And so the arctangent of x is itself equal to f of x, which is equal to this series here. And now it is very easy to proceed. We just need to put x equals 1. And as the arctan of 1, so there's a small typo here, this should be tan inverse of 1. So as the tan inverse of 1 equals pi over 4, this means that it is indeed true that this series on the left is the series is equal to pi over 4. So this gives us an increased confidence in the truth of our assumptions about sine and cosine being factorized, but although this is not a proof in any way, of course. So now we are going to find some more evaluations of these numbers E0, E2, E4, and so on by cross-multiplying the series for cosine and this series and equating it to 1 and then equating coefficients. And when we do this, we find that E0 equals E2 equals 1, and E4 equals 5, E6 equals 61, and E8 equals 1385, and so on. So we can go on as much as we want. And so if our formula for this series is indeed correct, then we would have the following evaluations. So very nice, it corresponds to, so for the zeta function, we were able to sum it when the exponents were even, but here we are able to sum these series when the exponents are odd. So that is very interesting. And in the next videos, we are going to probably study these Euler numbers further, and of course, the zeta function itself.